Log on, tune in, find out. Another good idea from Cambridge.
And he's going to speak on moduli of real and quaternionic vector bundles over a curve.
Thank you very much. Before I start, I would like to thank the organizers for giving me the opportunity to speak here today. So the theme I would like to talk about is a work that finds its roots, its inspiration in the work of Nanko and Melissa that we have just heard about. So as Nanko told us, well, what her and Melissa did is study flat bundles over a non-orientable surface S, and one way to interpret the result is to, or even to the way that Nanko just mentioned, the way they actually work with it, is to move back to the orientable cover M of S. And then the class of bundles that they study is bundles fixed by an involution, namely a bundle E over M, which is stabilized by this transformation. Okay, so for this to work, it was crucial that M was a Riemann surface, or what is the same saying that the non-orientable surface you start with has no boundary. So the observation that we can make, and that I will use as a starting point, is that if you put some extra structure on S, then you may get rid of the assumption that S has no boundary. Basically, the idea is to start with, or to endow S with a Klein structure. This simply means seeing S as the quotient, this time not of differentiable manifold with an orientation and an orientation reversing involution, but really start with the quotient of a Riemann surface by an anti-holomorphic involution. And this should be thought of as part of the structure on S. That the Riemann surface on M is fixed. It doesn't come later. So then, so first, what is a Klein structure? It simply means that on your differentiable manifold, you have an atlas whose the transition charts of which are either holomorphic or anti-holomorphic on a given connected open set. So such a map is called a D-analytic map. Or, so Klein structure may also be called a D-analytic structure. And then the point is that if you look at bundles over S in this D-analytic category, well then, by pullback, you get a holomorphic bundle over M. And more than that, this pullback bundle has what's called a real structure in the sense of a TIA, namely that the involution sigma twiddle here covering the anti-holomorphic involution sigma of M is a real structure. So it means that this diagram is commutative and that sigma twiddle is C antilinear. And that the square of sigma twiddle is the identity of E, of the pullback bundle, sorry.
Sigma twiddle on the...
Thank you. Yes. Okay. So this is a notion of real bundle due to a T. So if we try to think of this condition, then in this context it becomes that I'm sorry, I should have denoted this Q, and then E will be the pullback of Q. By the projection. So then in this context, the isomorphism of holomorphic bundles that we have is between the conjugate pullback of E and E itself. Yes, and so this is where the so this condition shows that what I'm talking about here is not a generalization of Nanko and Melissa's work, rather an analog. So any results I will talk about is not a generalization of the result, it's just something similar. Basically, the involution that we define on the space of connections is different from the one of Nanko and Melissa's. Okay, so in fact, this construction here between the analytic bundles over S and real holomorphic bundles over M is an equivalence of categories. So if you want to study the analytic bundles over a Klein surface, you may as well choose to study real holomorphic bundles on a Riemann surface. It's the same. And this is what I will do. Okay, so sorry. This should have been one. Then in two, I want to make some comments on real algebraic geometry, where this notion of real holomorphic bundles originates. Okay, so this is very easy. If you consider a real algebraic curve, so to me that's just a scheme over R whose set of complex points is smooth projective, so a Riemann surface, compact Riemann surface. Then, yeah, let me give you an example. So let's take the easiest real algebraic curves, the projective line. So such a curve, you have a complexification procedure. It just takes you to P1C, and the set of complex points of X or its complexification is just the Riemann sphere. So because C has an action of the Galois group of C over R, so an anti-holomorphic involution, it's just Z goes to its complex conjugate. Any complexification of a scheme over R inherits an action of the Galois group as well, which is continuous. So it preserves the set of closed points, as in this picture. And the involution in this case is simply, on the Riemann sphere, is simply the reflection through the equator. Okay? So let me denote this sigma. So here, the set of real points of x is identified with the fixed point set of sigma, and the set of closed points of the original scheme is by definition, or not by definition, but it's a property that it's the quotient of the set of closed points of the complexification by the Galois action. And this gives you, in this case, a closed disk. So it's a surface with, which is orientable and has a boundary. So how does these generalities on real algebraic geometry relate to that? Well, it's just that if we want to study if we want to study vector bundles over a compact connected surface which is either non-orientable or has a boundary, one way to do it is to say that the surface is the set of closed points of a real algebraic curve. And this gives you an idea to how to study bundles over that. Okay, so let me give more examples to illustrate this. Again, in the genus 0 case, there is one more possible involution, namely the antipodal map, and this gives you as a quotient RP2. So RP2 is the set of closed points of a real algebraic curve. In genus 1 case, so there are three classes of involution on torus. You have something similar to this one, which is some reflection through a point, which you have to imagine is here. Then in this case, so this is always x of c in this column, the set of complex points. Here, what you get as a quotient is the Klein-Bartel. Then you have another involution, which would be the reflection through this axis in the torus. In this case, the quotient is the Möbius strip, and finally you have one more involution, which corresponds to a reflection which fixes these two circles on the torus, and then in this case, the set of closed points is a cylinder. So it's interesting because already here we obtain all kinds of compact connected surfaces which are either non-orientable or with boundary. This one is non-orientable, no boundary, non-orientable with boundary, and orientable, no boundary. So, and this is a general thing. I'm sorry? Orientable, no boundary. Boundary. Thank you. Thank you. Sorry. Okay. The point is that any compact surface which is either non-connected, either non-orientable or with boundary may be interpreted as the set of closed points of a real algebraic curve. So this gives you a way to study bundles over that. Okay, why? Because then if you have a real algebraic bundle over a real algebraic curve, then this bundle of complex points is a holomorphic bundle over x of c. Sorry, let me write it this way, because it's of course more than that. It's a real bundle in the sense of a tier. Okay, and again this is an equivalence of categories. So we may choose any of these 3 point of views, either the analytic bundles or real bundles in the sense of a tier, or real algebraic bundles over X. Okay, so whichever point of view we choose, if we want to talk about moduli of such bundles, we need to come up with some kind of stability notion. So either in this context or that one, the stability notion is to ask that for any sub-object of a real bundle, so this means a bundle which is itself real. So if you think of the Atiyah description, it means stable under sigma twiddle. To have such a subbundle, it is itself a subbundle because the restriction of sigma twiddle to F is a real structure. And then the condition, the stability condition, is that the slope be strictly smaller than the slope of E. Okay, so then you get semi-stable replacing a strict inequality with the large one. Okay. So this E in the pair E sigma twiddle is always a holomorphic bundle, but if it is stable as a real bundle in the sense of this definition, it is not necessarily stable in as a holomorphic bundle. It is though when the rank and degree are assumed to be coprime. But let me give you an example of a real bundle which is stable in this sense and not stable in the usual sense. Well, consider F stable and E the direct sum of F and its conjugate pulled back by sigma. This is of course a real bundle. You just send V1, V2 to V2, V1. And well, it cannot be stable as a holomorphic bundle because it's a direct sum. But it is stable as a real bundles because a subbundle is of this form. And this has the same slope as F prime, and by the stability assumption on F, this is strictly smaller than the slope of F, which is equal to the slope of E. Okay, so a stable real bundle is not necessarily stable as a holomorphic bundle. Okay. So if you have this notion in mind, and with this remark, you understand that constructing moduli varieties for such objects may be a bit tricky. Actually, I think this is, if you really put the definition this way and have this in mind, this is still open. How to construct moduli varieties for such objects. The closest as far as I understand, the closest result in this direction is the paper by Biswas, Urtubis, and Oisman, and to which I will be referring a lot today. Okay. So let me try another point of view. which also has to do with real algebraic geometry. So namely, if we assume that X is defined over R, the usual Moduli variety for holomorphic vector bundles of rank R and degree D over X of C so this parameterizes S equivalence classes of semi-stable holomorphic vector bundles of rank R and degree D over the Riemann surface X of C. But because X is defined over R, this also has a real structure, a Galois action. So in other words, the coarse moduli scheme, which parameterizes those S equivalence classes, is in fact defined over R. So in this case, we can make this very explicit because so an element in this Moduli variety is an S equivalence class of a semi-stable bundle, and we will see that this map is a well-defined anti-holomorphic involution, so it's a Galois action. Okay, so there are some things to be checked here, namely that the involution is well-defined. It takes the S equivalence class of a semi-stable bundle to the S equivalence class of this one. Well, first there are good hints for that because this functor, which takes a holomorphic vector bundle of rank R and degree D, preserves the rank and the degree. So this is the point of conjugating the complex structure, is that you preserve the degree. And then if you preserve the rank and degree, you also preserve the stability or semi-stability condition. Okay. So we do have a real structure on the complex Moduli variety. So by definition, the real points of this moduli scheme are the fixed points of the Galois action. And then the question in which I'm interested is to know what can one say about this set, mostly about the topology of this set. And by that today I will only refer to connected components. So what can we say about the connected components? Can we count them and can we describe them in a way? So just to mention the connection with the Moduli problem here, if you assume that R and D are co-prime, or what amounts to if you restrict your attention to moduli of stable bundles, and consider the real points, so only stable bundles, then these are isomorphism classes of bundles which are both stable and real. And we've seen that is strictly included in the set of isomorphism classes of stable real bundles. Okay, so let me call this, when it's both stable and real, it's a geometrically stable real bundle, as opposed to a stable real bundle. So it's just geometrically because it's the set of complex points which is assumed to be stable. So it's a common expression in algebraic geometry. Okay, so as I said, this is understanding moduli of this is, I believe, a more difficult problem. So I will. Yes. I'm sorry?
What do you mean in that side? Because there is a natural isomorphism that respects
Right.
evolution or not. I guess.
Yeah, I forgot to define it, and you're right. The isomorphism class should respect the involution.
But then why should that be an inclusion? I mean, these are.
Because of this example, right?
No, but as classes, the group quotienting there can be actually smaller. So
That's a good point.
I guess you can just quotient by the same isomorphism classes. If you want to talk about that inclusion as.
Right. I never thought of it that way, but yes, it could be that. Okay, so I need to make this notion more
To
precise.
make sense of that statement, I think we just really need to talk isomorphism classes as bundles, not respecting the size of the other side.
Okay, so that would yield an equality here.
No, that gives you sort of makes sense of an inclusion. Otherwise,
Right.
you do have a map from that set to
Oh,
that.
right. Yes, of course. You're right. Thank you. Yeah, so let's put it as a map. Okay. Okay, so first let's try to understand a little bit those real points. I said that there were the fixed points of the Galois action. But as the case of line bundles already shows, an element, so which is a real point in of this moduli scheme, well, comes from, by definition, I will still assume that I am in a stable case because it makes it a bit easier to describe. So this comes from E, which satisfies this relation, namely that the conjugate pullback is isomorphic to E itself. But as it turns out, this condition is not equivalent to being a real bundle in the sense of a TIA. If you are a real bundle in the sense of a TIA, then you are a fixed point of this, but not the other way around. Even if the bundle is assumed to be stable. So to show you what can happen is just that you have another notion of a bundle which you can define, which you may define on M with an involution, a Riemann surface with an anti-holomorphic involution. It's a quaternionic bundle. So it's the same as a real bundle, except that This time, the automorphism sigma twiddle squares to minus the identity. And then if you have such a bundle, it is also isomorphic to its conjugate pullback. Okay. But if you have these two bundles, then there's a lemma proved by Biswas-Urtubise and Neumann saying that if E is stable, in fact simple, and isomorphic to its conjugate pullback, then E is either stable or real and cannot be both. Real or quaternionic, and not both. So this is important because here in this example, you may also have a quaternionic structure. You just define V1, V2 goes to minus V2, V1, and then you get an object which is quaternionic. So you really have to be careful with these objects. Okay. So I think, yeah. Now I can state the main result that I would like to present today. So, I completely forgot something. The reason why I was talking about real algebraic geometry and real algebraic curves in particular is because their topological invariance will be useful in the statement of the theorem. So I should recall the classification, topological classification of real algebraic curves, which is due to Klein. So I'll think of a real algebraic curve as the Riemann surface with an anti-holomorphic involution. And this is topologically classified by three integers. So G is the genus of M. K is the number of connected components of the fixed point set of sigma. And A is a mod 2 integer, really, which is 0 if M mod sigma is orientable, and 1 if it is not. So it's also the same as saying that A is 2 minus the number of connected components of M set minus M sigma. Okay. And then these invariants are subject to the following conditions: that first K is smaller than 0, greater than 0, smaller than G plus 1. This is the theorem due to Harnack. Then that, if K is 0, A has to be 1. And if K is G plus 1, A has to be 0. And finally, if A is 0, then K is congruent to G plus 1 mod 2. So if you have three integers like this, GKA, satisfying these conditions, there exists a real algebraic curve with those invariants. Okay, so let me try to say this correctly. So X is a real algebraic curve. Mx or D is the coarse moduli scheme parametrizing S equivalence classes of geometrically semi-stable algebraic vector bundles of rank R and degree D over X. Okay? And then I will assume that X is a topological type GKA. Then first, if K is non-zero, then if R and D are both even, the set of real points of this moduli scheme has 2 to the k minus 1 plus 1 connected components, non-empty. Well, in all other cases, and this set of real points has one connected component.
No, what is geometrically semi-stable?
I'm sorry?
Did you say geometrically semi-stable?
Yes, so the underlying so if you think of bundles like this, it's a pair E sigma twiddle such that E is stable in the usual sense. So this is to get a subspace of this.
But that was, I mean, sort of when you said geometrically stable, but geometrically semi-stable is just the same?
Yes. So geometrically means just that the set of complex points is either stable or semi-stable. So it's the condition on the underlying holomorphic bundle if you think of real bundles in the sense of a T.
That includes your actually being, that includes the ones that are stable in this weaker sense, because being semi-stable in this weaker sense, I think should imply being semi-stable in this other.
Oh, interesting.
Okay, that's another.
Interesting. It might be true. Yes. Mm-hmm. Nice. Okay. Thank you. Okay, and then the remaining cases. So this is when the curve has no real points. Then the conditions are a bit difficult to write down. So if this integer is even, and the degree is even, we have two non-empty connected components. And for fixed R and D, they are homeomorphic. Oh, forgot to say something up there. Then here, if this is even and D is odd, then the set of real points is actually empty. And then if Rg minus 1 is odd, well, we get one connected component. Okay, and I forgot to say here that between these 2 to the k minus 1 plus 1 connected components, there are 2 to the k minus 1 of them which are homeomorphic, pairwise homeomorphic, and the other one is not homeomorphic to the previous ones. So this needs some explaining. To understand why there are two types. Well, it's just that here we have 2 to the k minus 1 components of real bundles and 1 component of quaternionic bundles. And the real ones are pairwise homeomorphic, the real components, and the quaternionic component is not homeomorphic to the other one. Here only 1 connected components, so these are actually all real, I think. No, either real or quaternionic, it depends. Here there is exactly 1 real and 1 quaternionic, here no component, and here there's a real component if D is even and a quaternionic component if D is odd. So what's to be, so unfortunately with so many cases the theorem I think is a bit hard to state and to grasp. So the point is that we can count them, that the count only involves the real invariance of the topological invariance of the curve and of the bundles, so G, K, A, R, and D, and that we can describe the components, which we know which ones are real, which ones are quaternionic, correspond to real, which one corresponds to quaternionic. Okay, and as a corollary, we get, using Harnack's theorem, that the number of connected components of the set of real points in the Moduli space is always lower than 2 to the G plus 1 because of this Harnack inequality here. Just look at the cases and you get this. So this is, I think, better to get the first idea. Okay, so this, no. So I think I'll try to say a word on strategy to prove this result. So this is just using the Atiyah-Bott description of the Moduli space and involutions just as in non-post-Hope. So maybe I can be brief on this. Okay. So what I will briefly describe is the momentum map picture of Atiyah, Bott, and Donaldson for these questions. So this is just obtained the following way. You fix a Hermitian vector bundle of rank R in degree D, look at the space of connections on it. There's a unitary gauge group and its complexification, which is the set of complex linear endomorphisms of E. And then the basic fact is that holomorphic structures on E are the same as orbits of unitary connections under the action of the complexified gauge group. So the correspondence goes this way. If you have a unitary connection or the associated covariant derivative, you define the holomorphic sections of E to be the elements in the kernel of that differential operator. Not that one precisely, but rather its 0-1 part. Okay. So the point is, if you have a bundle, a homomorphic vector bundle E, it determines an orbit of unitary connections under the action of the complexified gauge group. Okay, and then, well, Donaldson theorem characterizes precisely which connections correspond to stable homomorphic structures. So E is stable if and only if the corresponding orbit of unitary connections contains what is called an irreducible Young-Mills connection. So there are two conditions. First, irreducibility. It means that the stabilizer of A, connection A, inside the complex gauge group is as small as can be, namely C star. And a Young-Mills connection, so this will be a bit different from the definition Uncle gave you. I'm actually assuming that actually for reducible it's the same. Assuming that the curvature is the Hodge star of a scalar matrix. Okay. Oh, and there's an important point. So this is 1, this is 2. An important point is that Donaldson obtains unicity modulo unitary gauge. So in particular, if you have a Young-Mills connection, its stabilizer is actually contained in S1, or is actually S1. Okay. So it's rather but from this theorem we get that the set of graded isomorphism classes of polystable bundles, so direct sums of stable bundles of the same slope, are exactly connections which satisfy condition 2 here. So the curvature is diagonal. Forget about irreducibility, and then think of F as the curvature map. So what I'm saying is that the pre-image of this diagonal matrix modeled by the gauge equivalence is the set of graded isomorphism classes of polystable bundles of rank R and degree D. So again, this is a direct sum of stable bundles of slope D over R. But then by Seshadri's theorem, this is exactly the set of S equivalence classes of semi-stable bundles of rank R and degree D. Okay, so this is our moduli variety. Okay. So then, what's the strategy that I promised to explain is well, to characterize, well, we'll see that on the space of unitary connections, A sub E, there's a finite family of real structures whose fixed points characterize exactly the unitary connections defining real and quaternionic structures on a fixed Hermitian bundle. Plus there are compatible involutions on the unitary gauge group and the dual of its algebra, such that connected components of the set of real points are the associated Lagrangian quotients. So let me make this precise. There exists a finite family of real structures on the space of unitary connections and compatible involutions of the unitary gauge group and the dual of its algebra, which is just a space of two forms and with value in the adjoint bundle, such that all induced by the choice of a real or quaternionic Hermitian structure on this Hermitian bundle E. So at T above, to obtain the description of homomorphic structures in terms of unitary connections, fix a Hermitian bundle. Here we fix a Hermitian bundle plus a real or quaternionic structure in the Hermitian sense. So it's an isometry, but the bundle is no longer holomorphic. It's just a complex vector bundle. Okay. And then you get two things. Well, you get mostly that the associated Lagrangian quotient, which is by definition the quotient of the invariant elements in the fiber of the momentum map, modeled out by the action of what I'll call the real gauge group. So the fixed point set of the involution on the unitary gauge group are the connected components of the set of real points of the moduli scheme of semi-stable bundles. Okay, so let me first define the involution. So fix a real or quaternionic Hermitian bundle, E sigma twiddle. Then this bundle, conjugate pullback of E, the complex vector bundle E, is isomorphic as a Hermitian bundle to bundle E. Let's call phi the map, which is the isomorphism. And then, if A is a connection on E, we define A bar by the following condition. So on a section of E, it's just, well, I take a section of E to a section of the conjugate pullback bundle by the inverse of the isomorphism phi. Then on this conjugate pullback bundle, I have, let's call it a conjugate pullback connection, sigma star of A bar. So I may derive the section with respect to this, get a one form with value in this bundle, and I push it back by the isomorphism phi, and I get a one form with value in E. So this is indeed a connection on E. Okay. Well, first, well, this is very similar, this formula is just similar to the gauge action, except that phi is not an endomorphism of a bundle, but an isomorphism between two distinct bundles. But it's the same formula. And in particular, you may write A bar following way. So this is similar to the gauge action. And then with the slightly abusive notation, you see that it is an involution, that this correspondence is an involution, because if you take A bar bar, it's just phi conjugate pullback of all this and then this is phi's conjugate pullback of phi A and the inverse of the previous one. But then here, well, the conjugate pullback of this map is a map from E to the conjugate pullback of E, and it's either plus or minus phi inverse, depending on whether sigma twiddle is real or quaternionic. So here you get plus or minus the identity, here you get plus or minus the identity, the same signs, so they cancel out and you always get A here. So the point is that even if sigma twiddle is quaternionic, you do get an involution on the space of connections. And this is a good involution because A defines real or quaternionic holomorphic structure on the Hermitian bundle E sigma twiddle if and only if A is fixed by this involution. So why is that? Well, because to define a real or quaternionic structure on E, you have the covariant derivative, which says sections to one forms of E, and then because E is real or quaternionic, this has a real or quaternionic structure, and this also. And the connection dA will define a real or quaternionic structure if and only if it commutes to the respective structures, because in this case the kernel of the 0,1 part is stable by the real structure, so it has an induced real structure, and this means exactly means that the bundle is real or quaternionic. And then it's just the involution is designed to make this dA commute with the real structures. Okay, so just to finish, the The implication of that is that to get all the real points of the moduli scheme Mx, what you need to do is to consider equivalent classes of real or quaternionic structures on the Hermitian bundle E. And in fact these are exactly the connected components. So there's a lot of work obviously to show that these are the connected components. But then the point is that if you want to count the connected components of that, all you need to do is count the topological types. And this is just using the theorem of Bieswas-Urtubise and Huysman, because for instance, let's look at so K positive, R and D even. Well, okay. Factors, well, okay, doesn't matter. Then, I didn't state it. I'm sorry. There's a theorem by Bieswas, Urtubise and Huysman, which gives exactly the topological classification of real or quaternionic bundles. So let's take this case, a real bundle over a curve with real points. It's topologically classified by, of course, its rank and its degree, and K Stiefel-Whitney classes, which are just the Stiefel-Whitney classes of this bundle. So the fixed points of sigma twiddle define a vector bundle over the fixed points of M, and this is just a union of circles. So in each, over each circle I get a Stiefel-Whitney class, and I call them W1 to WK. And the condition is that D mod 2 should be equal to the sum of the WKs. And then, so actually the result is complete. It classifies also the other topological types of real and quaternionic bundles. The point is that now if you want to count the topological types, you just have to count the solutions to this equation. And this is exactly 2 to the k minus 1. D is fixed, and then if you want to get a solution here, you only have to choose the first k minus 1, and then the other one is imposed. So there are 2 to the k minus 1 topological types of real bundles. So it goes the same way in the other cases. Just to conclude, why are 2 of these connected components homeomorphic? Well, take a real bundle and take the tensor product by a line bundle with the correct topological invariance so as to modify this one, these ones. So this is how you move from one connected component to the other, and it's no homeomorphism. So this gives also an intuition why it doesn't work in the quaternionic case, because when k is not 0, there cannot exist quaternionic light bundles. Homeomorphism. Okay, I was a bit over time, sorry. I'll stop here. Thank you.
Questions?
So if you compute the number of components for the fixed determinant, should be seen.
I did not. What does change? There should be a similar description. I'm not quite aware of it, but yeah, I would expect it to work somewhat similarly.
I'll ask you the sort of reverse question to what I asked to Nankuo. So is there any interpretation of this Moduli spaces in terms of representations of
Yes.
the fundamental group?
Yes, there is. So this is also actually, I should not erase their names because it's also a result of Biswas of and Neutzmann. Who show that so there's a bijection between a set of real points and representation of the orbifold fundamental group of X. So by definition, not by definition, but this group is a group that fits into this following exact sequence. So this is the Galois group. This is the usual topological group. And a representation of this, by definition, is a series of three maps. One of them is identity. Okay. So, allowed by equivalence of representations. So if you look at representations of the orbifold fundamental group in this sense, so meaning mapping of this exact sequence into this one, then the set of equivalence classes of this is in bijection with this, with the set of real points. So this is the real version of the Neurosemann-Schaffhauser correspondence in the sense of Biswas to be as nice. So this group is important because, well, first of all, if the Riemann surface has, if the involution of the Riemann surface has no fixed points, this is just the ordinary fundamental group of the quotient. But if the quotient has a boundary, you do not get the same object. You don't get the topological fundamental group. But in any case, the orbifold fundamental group is the group whose profinite completion is actually the algebraic fundamental group of the real algebraic curve underlying the whole theory.
Can you give its presentation, the orbifold fundamental group? So we have a presentation for the topological fundamental group. It's basically 2G generators and.
Well, so first of all, elements of the orbifold fundamental groups are not loops. If you look at them in the Riemann surface, there are either loops from the base point to itself, or a path from X to sigma of X. So these.
So they basically get identified as loops in the quotient.
Yes, absolutely, absolutely. And I think the presentation that you get is similar to the one that Nankuo used in her talk. After all, when there is no boundary, this is just the same group, and there would be something similar. I think in the paper of Biswas to be the nice one, there is a presentation, but I'm not quite sure now.
The case in which you get just a surface, this is just given by a bunch of points on the surface and some integers, right? And so, I mean,
So the additional generators are basically loops
loops
around
the
orbifold points.
with prescribed monodromy,
Uh-huh.
which is dividing by the integer. So it's like,
Okay, so it's-
as defined in the previous talk on Thursday by Simpson. This refers to that.
okay, so it's
Okay.